Hey guys, this is Dr. Aeronautics, and we're back in space exactly where we left off. If you don't know how to get to this point, watch my previous tutorial on how to achieve an orbit, and you'll end up exactly where we are now. The reason we're still here is because what we're going to do next is applicable to this tutorial, which is orbital maneuvers. You remember I said that an orbit is what you use to get from point A to point B in space. So how do we do this point A to point B thing? There are three types of maneuvers and their negatives that you can do. You can do a in velocity vector burn, and the forward is prograde and the backward is retrograde. A prograde burn, let's see, it looks like it's nighttime, so that's no good. A prograde burn would be using the main engines. To the perspective of the viewer, we're going straight into the screen towards that cross, and retrograde would be straight out of the screen using our retro engines. By definition, you have to be exactly on the prograde or retrograde velocity vectors in order for that to happen. And we have buttons to do that. I can actually demonstrate this right now. If I press Pro G, that's going to turn us prograde. So now if we want to do a prograde burn, we can do it right now. They cancel that. Now if I press Ret G, that's going to put us in the retrograde position. So we're actually going to be lined up to do a retrograde burn with our main engines. Sometimes this is useful when you're doing a re-entry burn. It's pretty much necessary when you're doing a capture burn due to the amount of delta V involved. You can't use your retro engine because they're simply not powerful enough. You're not going to get into orbit fast enough given how low the approach typically is. Alright, and as I can see here, we have a type of planet here that's Jupiter and Saturn. We can fly there. I just want to mention that. We could fly there right now, but we're not going to. Okay. So now if I lit up the main engines, we'd be doing a retrograde burn. So if I did a retrograde burn from where I am right now, we would re-enter, because it would essentially slow us down. We'd go back into the atmosphere, and we'd probably end up landing somewhere in the Pacific Ocean. So we're not going to do that. Okay, the second species of burns that we can do are the plane change burns. And those are done at orbit normals. So orbit normal plus and normal minus. It's called normal because this this tape that we've been rotating around, this yaw tape here, which I'm now moving around, is the orbit plane. So in order to turn normal to the plane, you have to go straight out or straight up and out or straight down and out. So there's buttons for this too. This is the normal plus, NML plus. And what it's going to do is it's going to rotate us all the way up to 90 degrees. If you heard of Apollo lock or gimbal lock in Apollo, this actually wasn't where you get gimbal lock. We have a different coordinate system. I'm going to explain about where Apollo used to get gimbal lock a little bit later. Okay, so we're now at orbit normal plus. If we did a burn here when we were north of the equator, we would be increasing our inclination. We would, if you look at the orbital swing, we don't quite get far north enough to reach Los Angeles. So if we wanted to reach Los Angeles while north of the north equator, let me think here. Now it's actually going to be whenever you have a positive direction here, if you burn orbit normal plus, you'll bring the swing further and further north. And if we did it, eventually we could reach Seattle and Vancouver and Nuke if we were really crazy. Okay, but right now we're on a slight downward trajectory. So we'll do the negative of that, which is the orbit normal minus. And what that's going to do is that's going to, when you have a southerly trajectory, if you burn southwards, or orbit normal minus, if you have a prograde orbit, then you will go further south. Like, for example, I can't reach Woomera where I am right now. If we burned where I am right now at the orbit normal minus, we could eventually reach Woomera, and I need to get a New Zealand base. I need to get an Antarctic base. Eventually you would reach Auckland, and then what comes next? Wellington and Christchurch, and if I keep going, eventually we'd reach McMurdo. Yeah, base McMurdo. So, what can we do now? Alright, so the last two types of maneuvers that we do are rather inefficient, and they don't have they do not have autopilots to put you where you want to go. So we have to navigate there manually. And this is the Apollo region of gimbal lock. There's no such thing as gimbal lock now because we use a combination of sensors. And this is common even in the satellites of today, not like crazy space planes from the future. Like modern day satellites like Cassini and New Horizons, they could navigate anywhere. They didn't have that gimbal lock problem. Okay, so we're approaching the region of interest. So this is a yaw of 90 degrees and a pitch of 0 degrees right here. So this is in the orbital plane, but it's outward from the prograde velocity vector by exactly 90 degrees. So by definition, this is called the outward burn. And what this does is it rotates the highest and lowest points of the orbit. As a matter of fact, we actually happen to be at the lowest point of orbit. So if you watch the lowest point of the orbit, you're going to see the hollow circle representing the highest point of the orbit, and the solid circle representing the lowest point of the orbit swing around without changing altitude. So check this out. Look at that. So that will mainly swing what's called an apsid line. If you drew an imaginary line, let's get rid of this. You drew an imaginary line from the top of the diagram where the filled circle is to the bottom of the diagram where the hollow circle is. That's your line of apsids. It's between your periapsis and apoapsis. So let's say we didn't want to do that. Well, I'm going to rotate us around to 270 degrees, coming up on prograde now, just past the prograde velocity vector there. And notice I'm going to begin adding retro thrust now to slow us down, to get us up to precisely where we want to be. And I'm doing this manually because I said there were no autopilots for this. Okay. And we just burn again in the negative direction, and you're going to slide them back to where they were. There you go. Okay, so what are the regions of interest for the other maneuvers that we can do. For an outward burn, it's not normally considered efficient, so we try and avoid doing them. They're mainly done for timing reasons, and the burn would be dependent on the situation every time. For the let's do the apoapsis and periapsis burns next. So if you're going to do a prograde or a retrograde burn, what you're doing is you're changing your scheme of altitudes. So one of these ones that we can do is what's called a home-in transfer, which is you go further out or further in, depending on the circumstances, and then you circularize. Those are doing all. If you're raising your orbit, it's using all progrades. If you're lowering your orbit, it's all retrogrades. So if you're doing your progrades, you want to burn at the lowest point of the orbit, which is the, for us, it's the perigee. And to do a retrograde burn, you want to burn at the highest point of the orbit, which is the apogee, over here. That's a effect called the Oberth effect, which basically states, I'm not going to get into it, but it basically states the higher you are, or rather the lower you are, the higher the outward velocity at infinity will be. You don't have to worry about that. We'll take care of that later. Okay, so it says we're about 106 seconds out to our periapsis. Perigee, so we're gonna do this pro G. We're gonna raise our orbit. So meanwhile, I'm gonna create a dummy satellite that we're gonna target. Okay, I've created a dummy system. We're not gonna make a full rendezvous approach, but we're at minus 60 seconds. So how do we find this thing? We're gonna do target, down arrow to spacecraft, right arrow, and down to dummy. Press enter. Now we've selected it. Now take a look at the altitude. Sometimes you'll have to change the projection in order to see it properly, but we're going to be able to target it regardless, because you notice it's at 637 kilometers. So we have the autopilot on, and we're looks like 20 seconds out from the perigee, which is the most efficient time to do this burn. So we're going to burn until the apoapsis reaches 637 kilometers, and it should go very quick. Ideally, you want to center on the time, so I'm actually going to start the burn about 5 seconds early, estimating that the burn is going to take about 10 seconds. Okay, I just cut the engines off. So now you can see our apoapsis altitude is 652. Our periapsis altitude did not change. So let's make that disappear. Now you should be able to physically see the fact that we are going a lot higher above the surface of the Earth on this side, and we're not as high on this side. So in order to fix that, we have to do a circularization burn. That's again going to be a prograde burn. So in order to fast forward time, what we're going to do is we're going to disable this Pro G. I'm going to save my progress because Orbiter is notorious for being a C++ program and that it crashes a lot. Okay, and let's go forward in time. So this is 10 times the normal rate. That's pressed by T. T again, now we're at 100 times the normal passage of time. So basically what we're doing is an untargeted home-in transfer. This is the most efficient way of, well, it's the second most efficient way. It's the most efficient combination of time and energy in order to get you. The bi-elliptic is actually the most efficient orbit, but unless you're doing something in a high gravity well where things occur very fast, it's just not a smart idea to do it. Also, I like to have my HUD color on green. There we go. For space maneuvers. I don't know why it's still red. Turn these things back on. So we're about 150 seconds away. There's a nice view of the Caribbean. And notice the point that we did the maneuver. It just so happens that the highest part is over where we took off from. Now, I'm not going to zoom in because it crashed the video last time, but it was right about there. Wow, is that a... that looks like a hurricane. Holy cow. So there's a hurricane over North Carolina. Now you can see, if I zoom in, look at how much we can see now. Remember before I said we could only see about the size of Australia? Well, we're a lot higher now. We can see almost of large point of continental North America. Let's see, we've got about 50 seconds of the burn now. That's beautiful. Let's go ahead and turn prograde. We're going to do what's called a circularization now. This is so that we stay up here in this orbit that we've chosen. And because of the O-berth effect, actually it's not the O-berth effect, it's simply the fact that Earth's gravity is weaker because we're further away from it. The burn is going to be even faster. I'm going to say it's going to be about 6 seconds. So to center that, we're going to do this about 3 seconds out from apoapsis. So watch that perigee altitude. We're going to burn until you see 640. Whoops, that's 540. Right there, 640. In fact, I overshot to 657. Precision is not important in this exercise. It's simply a demonstration. Let's turn back while we plan the next part. Let's see. I'm going to estimate, based on the coverage of land, that most of the people are going to be living up this way. So if you want to spot your house, let's see here. Fit as much on the screen as I can. In a normal spacecraft, you don't have the freedom to be able to do stuff like this. Normally you have to be facing a particular direction due to temperatures and whatnot. Alright, so let's see where this thing actually is. Find the dummy again. Okay, so the dummy happens to be exactly opposite of where we are. It's over here. So that's not a good thing if we want to sync up with it. So let's say we want to find this thing. You notice now our orbit plane is on the screen. You see how it's flush against the screen, and it's even across the Earth. This thing's orbit plane is not. It goes in deep in the screen, and then it comes out high above the screen. So we have a difference in relative inclination. So to change a relative inclination burn, you need to do an orbit normal plus and orbit normal minus. That's how you change your orbit planes. So let's go ahead and target this thing. Actually, we'll go to select, and it's align planes. Now we're going to target spacecraft dummy, and now you find out we have a relative inclination. Oh, and look at that. We're at a descending node right now. So what does this mean? If we have to increase our relative inclination on a descending node, that means we're orbit normal plus. Now we're not going to be able to finish because it's a 600-second burn. But now I'm burning, and now you can see that starting to decrease. So that relative inclination difference is a fact of these dotted lines. You see this green dotted line and this yellow dotted line? When they're collinear, then you have no relative inclination. So again, what we're doing is we're changing our aiming so that our orbit moves in the same direction. Planar adjustments are sometimes unavoidable, but when you can avoid them, you have to avoid them. I'm going to do a really quick calculation right now, just to prove my point. Let's see, we want plane change. And what's involved with it is the semi-major axis of your orbit, which for me is 70,025,000. This is using a calculator which I developed. I was relatively smart when I was in school. Every homework assignment which was given to me, I decided to write down. Let me see, we're at 6,400 meters. Put in the mass of the Earth, and we have a relative inclination difference of 46.42 degrees. We'll just say 46 for now. There's no reason to get more precise than that because we're burning. So as a result, I put all these problems in one place, and that way I can solve the problem once. It's much faster the second time. I write all the steps down, and then it's just as simple as plugging it into the calculator. It's really useful. Let's see, I think I might have, yeah, I have too many zeros in here. 36. No, that's kilometers. 000. Aha, okay. So that we need the radius in meters. There we go. 70,11,000. I was giving it a value in the inner core. There we go. That's a lot more realistic. So now it's going to require 5,900 meters per second to bring this into check. Keep in mind, if you time this right on the Earth, it would be 0. If you remember how much delta V it takes to get into orbit, it's about 9,600 meters per second. So, we need basically 2/3 of an orbital rocket in order to do this maneuver. Now, with something that has enough fuel, such as the Delta glider, you can get away with this. But normally, you can't get away with this. So the rule is to lower relative inclination. You need to go the opposite way the node is, right? So the descending node means you're going down, right? So how do you slow something that's going down? Burning up, which is not burning up, but burning upwards in the direction that we are. If we were at the ascending node, your path, as shown, now this is a little bit different. In fact, let's target the dummy now so you can see where, there we go. You can see where it is. Yes, you can see now if I zoom in, we're on a downswing. Actually, no, that's it. Where are we? We should be just over the North Atlantic now, if I remember. It should be about here. Oh, yeah, there it is. Okay. Now, at whence time we passed, the node is when you cross the path. So that has actually happened so long ago it would have erased, but it would have looked something like this, right? And so we're descending. We're going below. We're going south of the curve. Here the curve is south of us, we're north. Here the curve is north of us, we're south. So by burning northwards, that's actually what it is. If I turned on constellations, look, here's the North Pole. By burning northwards, we're shallowing, or actually what we're doing is we're increasing. You can see this goes further north and further north. And if we were on the path, we would eventually go so far north that the planes would co-align. And you can now see, if you look at the orbit MFD, these two circles are getting closer to being co-planar. So to demonstrate the second part, what we're going to do is we're going to cut our engines now because it's extremely inefficient. And what we're going to do is we're going to wait for the ascending node. So this is where our path will now become northwards of this path, right? So if you're on an ascending node, that means you're going northwards, but you need the path to go southwards. So on an ascending node, you're going to burn southwards in order to lower the relative inclination. Now, let's see if we were doing it with the equator and we were trying to raise our relative inclination, right? Like, let's say we wanted to pass over South Africa. So let's select spaceports. Oh boy, let's see if I can remember what it was called. What's a good name in South Africa? Johannesburg? No. I might have to go down the list. Oh, that's cool. Taluan. I know where that is. Let's see here. Aha! I got it. Okay. So if you notice, it's at 34 degrees south. So our inclination is, actually it's 37. So it's a bad example. We can actually get there. Let's talk about something northward, right? Let's go for something really far up. Let's go spaceports. Let's go to the Cosmodrome, Baikonur. Baikonur is at 45.92 north, and we're at 37.17 on the highest of our swing. So we'll never reach Baikonur. In order to reach Baikonur, we're going to have to burn and change our relative inclination even higher. Like, for example, the ISS. The ISS has a 55-degree inclination. Look at how high that goes. That's how the Russia space probes can reach it, is because that's why the inclination is so high. If the inclination were lower, they'd have to do a costly plane change, and all of their orbital rockets would be the size of Saturn V's because of that. So in that situation, when you're going southwards, you want to go even more southwards. So you burn southwards, and as a consequence, it's like Newton's third law, right? If you go further southwards, you're also going to go further northwards. It just so happens that way. So when you get to the ascending node, you want to go further northwards when you're going north, so you burn up the ascending node. Wow, that didn't sound right. Well, wait for me to talk about the semi-lattice rectum. Yes, that's an actual location. It's a location that is actually out from the periapsis. So here's the periapsis. Draw a line straight to the center of the Earth, and now go out at exactly 90 degrees, which means right here, this is the semi-lattice rectum, and right here, this is the semi-lattice rectum. Don't ask me why they decided to call it that. Okay, so we're going to fast forward to our next node alignment. So let's go ahead and go back to align planes here. You notice it's saying kill thrust. because the most efficient places to burn are the descending and the ascending nodes, because you're trying to. It's very similar to your orbit, right? If you're trying to increase your highest point of the orbit, you want to burn at the lowest point, because otherwise all you're doing is you're moving a few hundred or thousand feet, and then eventually you'll get swung around with the gravity, and relative movements will become irrelevant. So likewise, we're at pretty much the northernmost location now. So if we burn our engines, that's just going to move us forward another few hundred feet, and then eventually the straight line will level out and we'll get swung around southward again. So never do a plane change unless it's hyper local. I'm talking like 0.02 degree plane change. Don't do that unless you're at a node. Remember, ascending node ascending node is up for raising, down for lowering. Descending is down for raising and up for lowering. So we're gonna go forward to the ascending node now. So here's 10 times acceleration. Here is 100 times acceleration. Over here, where this TN, this is your time to node. This is going to show us exactly how much time there is till a node. Now, because we are swinging this over the node, we want exactly half of that. So now I've gone down to 10 times. So even though it says 210 seconds, we're actually going to wait until the node time says 105 seconds, because it's supposed to be 105 on this side and 105 on that side. That will allow you to get a non-impulsive movement. So we're going to go all the way down to 105, but now at 200 I am going to move in the proper direction. So this is an ascending node, which means we need to burn southwards. So I'm going to disable that and do orbit normal minus. So we are 80 seconds away from the burn. So this is a little bit confusing, right? You see, it looks like we've already passed the node, but in reality, the spacecraft is in such a bad location that the current node is erased. In fact, you know what? I can fix this. We'll go to display orbit plane. There we go. That's what's actually going on. Now watch how this changes, right? The direction that we're burning is towards the South Pole. So the engine, it's going to be going down this way. So what's going to happen is, if you burn this way and your velocity vector is this way, you're going to get this to curve along here. That's what we're trying to do. Okay, 20 seconds out from the burn. This is going to be a long burn, so I'm going to go full thrust. There we go. That ticker will light up for your most efficient thrusting time. So if it's not efficient to burn, it won't tell you to burn. All right, let's take a look here and see what's going on. Turn off track so that you can see it moving. There you go. You see how this one is changing and this one is not? That tells you that he's not moving, but we are. Or, I'm sorry, we're all moving. But I'm the one accelerating. He is not. I've got my engines on. In fact, there was an article in Space News very recently about a about an interstellar object. It's that weird oblong red thing that appeared to be moving. It appeared to be essentially doing a burn, and so they were like, "How can this be?" Honestly, if you wanna ask me, I'm gonna say it's aliens. I really think that this device is a spacecraft in disguise from like another intelligent civilization. I think it's just, nonchalantly marching through the solar system until we can't detect it anymore. Then it's going to turn its engines on. Anyway, so this has happened in years past with other asteroids. Now this one's interstellar; it's different. But in the past, what it's actually been is a plume of ice has melted into a vapor, and the vapor jets off the side like a geyser, and it forms a little rocket, and that's what comets have done. Comets will change their orbits quite a bit because they have such long period orbits, and if you have a really large orbit, we'll demonstrate in a future episode. If you have a really large orbit with a very high eccentricity, I'm talking about 0.999, it's very, very easy to change your orbit. With, if an astronaut did as much as jump off of the side of it and then jetted back with his jetpack, that would greatly change its orbit. So some gas wafting off the side could do it. So if it's not a interstellar planetary ship, then that's what it would have to be. Okay, now look at how close we are. We're almost there. We're at 0.9, 0.8, getting ready to shut the engines down. 0.6, 0.5, 0.3, 0.2, 0.15, 0.07, 0.03. That's it, 0.01. That's close enough for a rendezvous should we want to do it. And now if I turn on... in fact, you know what? You can't even see the yellow line anymore. That's how close we are. We'd have to zoom in if you want to see it. Wow, look at how close that is. Kind of reminds me of those lines at Target on the wall. Okay. So, now what's going on? Now, we should be chasing each other around. So let's go to Orbit Map. Oh my goodness! We're almost exactly 180 degrees out of phase. That's remarkable. Remember what I said about the dotted lines? They're fully aligned. And look about the orbits. Both orbit directly all the way around. So look at that. I'm actually curious to see if this thing has any docking ports. Okay. Yeah, I didn't think so. Let's go back to the dummy here. Okay. Nope, it does not. Okay, so what happens, right? You could wait around, but the issue in waiting is the time it takes you to orbit is only related to your semi-major axis, right? So let's take a look at our semi-major axis. 7115, and the dummy is 70007. What that means is the orbital planes are pretty close together, right? So what are you looking for? You're looking for the least common multiple. And if you're talking for the least common multiple to two numbers that are extremely close together, It's going to take forever. So long that I'm actually going to say it's going to take 5 ever. Let's look for... I built an orbital timing calculator somewhere in here. Let's see. Maneuver timing. Nope. Let's see. Patch conic, home in. I guess I'd have to do orbital timing point to point. Well, that's no good. Alright, I'm going to have to build one real quick. Okay. So, the orbital period is 2 times the number pi times the square root of the semi-major axis cubed divided by, and this is inclusive, gravity, which is 6.67 times 10 to the minus 11 kilograms per newton meters second squared or something like that, times the mass of the Earth, which is 5.97 times 10 to the 24th. I don't have this information in front of me. This is doing endless calculations. And so what we find, we should get about 90 minutes, right? So this is going to be in meters. So it's 7114 kilometers, so add 3 zeros per meters. And what I find is 5,974 seconds. If I divide by 3,600 seconds per hour, that's 1.65 seconds. Actually, you know what? Let's divide by 60. That's what I'm familiar with. 60. I'm using Excel. 99 minutes. And that's exactly correct. Because our altitude is 700 and... we're at about 730 altitudes. Altitudes? What the heck? 730 kilometers. And I've worked with some spacecraft that are at 705, which have 99 minutes in the real life. So I have the calculation correct. So what I'm going to do now is copy it over. And we're going to say that this one is 70006, add 3 zeros for the meters, which means he has a 97-minute orbit. So let's see if Excel has an LCM. Here we go. The least common multiple of 99 and 97. 9,603. So it will take us about 96 orbits or let's see. Yeah, it will take approximately 96 orbits in order to synchronize. That is that's a long time. That's about 160 hours. It would take a week. It would take a week to synchronize. Ladies and gentlemen, that's unacceptable. Little quote from Apollo 13. Actually, no, it was gentlemen, that's unacceptable. But anyway, whatever. 60s. Okay, I actually at the time I think it was 70. I think it was like 70, 71. Let's see, consult my Apollo 13 chart over here. It was April 11th, 1970 was the date that the Saturn V launched. Okay, so what I'm going to do now, if you watch, I'll let you watch it for a little bit. What we're doing now is we're going to go around to our periapsis, because there are 2 solutions to this, right? One solution would be to lower our altitude so that our semi-major axis shrinks considerably, and we will get back to our position here much faster than it will. And eventually, you know, if we have a 90-minute orbit and it has a 97-minute orbit, it'll probably be about 8 orbits or something to sync up. If we did that, though, we would be re-entering. Our other option is to raise our orbit considerably and make our orbit 2 hours and its orbit 90 minutes. That will allow us to synchronize up in 4 orbits, and that's even better. So that's exactly what we're going to do. So in order to raise your orbit, you want to go for the lowest part of the orbit. We could burn anywhere because if you look at the difference, it's only about 60 kilometers. It doesn't make that much difference. But in order to reinforce the concept, I'm going to burn at the periapsis. So let's face the Earth after checking to make sure that we do not have any. Let's see. I think that's sunrise. Checking to make sure that we don't have any time acceleration, because you will get screwed if so. And we're going to swing around to the other side of the Earth, which is where our periapsis will be, which should be pretty close to dusk. Let's go to 10 times the normal rate. Oh, check this out. The ship will actually change color. See how it has that slight orange tint? It'll actually change color based on the color of the sun radiating out of the atmosphere, combined with the color of the Earth. Wow, is our prograde velocity vector going to cross the sun? Sure looks that way. It's going to be so close. Yeah, it's going to be a little bit off. I want to go to the sun. That's a great song. Not only because of how like actually good the song is, but because it's impossible. Well, it's not quite impossible, but it's really, 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 really hard. Because there's so much energy to kill off. It's so funny. You're actually better off going all the way up. Let's save real quick. Cannot save enough in Orbiter. Look at that cumulus cloud formation over the ocean. You're better off going all the way up to Neptune and then burning down until you've lowered your orbit into the sun. I think that's the easiest way to do it. Because otherwise you'd have to kill 620 kilometers per second. And although the Delta Glider has a lot, we only have about 20 some meters per second in total Delta V. So yeah, actually it's not 620, it's going to be closer to about 500. Because the orbital velocity in low sun orbit is 430 kilometers per second. On the Earth it's 7. So yeah, that just gives you an example. It's nearly impossible. Okay, so take a look at that orbit track. You see how we're basically chasing each other around? So we're basically never going to end up. I know that cloud formation, it's altocumulus. We're never going to catch up. Well, we will, but it'll take a full week. And again, that's unacceptable. So, alright, let's go to 100 times. Let's get to that perigee. Whoops. I thought I crashed the simulator. Okay. So that's what it looks like when you orbit 100 times faster. And boy, is it beautiful. I don't know what's going on, but my frame rate is now super high. It's actually at 60. Oh, look, we're over eastern North America again. Let's see what, I don't even know what we're looking at. There's too many clouds. Ah, okay, so here's Cape Hatteras. The northeast is going to be under this cloud cover. This is probably Baffin Bay. Or no, it's the Gulf of St. Lawrence is probably up here. Anyhow, we're almost there. See, that angle really hasn't changed much. So I think what we'll do is we'll just sync up with it, but we can't dock. I know I keep adding things up, but I really want to try and enforce the concept because I'm going to get enough questions until you get used to it. You need to see things enough times before you can recognize a pattern in what's going on. So that's basically what I'm trying to do, is I'm trying to establish a pattern that you can recognize. Okay, so here's what we're going to do. We're going to do, first go to prograde velocity vector, because we're going to raise the orbit at the lowest part of the orbit, the perigee, or periapsis colloquially. We're going to do sync orbit, target, spacecraft, dummy. And we've got no intersection. And that's fine. Oh my gosh, I sound like Neil deGrasse Tyson. That's fine. Okay, that was hilarious. He had this one quote. He was like, "Some like it small. That's fine, but I like it big." I forget what he was referencing, but it was pretty funny. I think it was intentionally made to sound that way. Let's see. So we don't want transfer quite yet. What is it? Sync? No. Yeah, we do want. I think we do want transfer. Target, spacecraft, dummy. Do HTO for hypothetical transfer orbit. And what we're going to do is we're going to increase our altitude here. And what it's going to tell us is that there's no intersection. Yeah, that's kind of annoying if it tells you that there's no intersection. You really need an intersection in order to get this thing to work. All right, screw it. Let's go to what is it? Transfer. We're coming up on periapsis now. We're going to go to sync orbit, change to ship periapsis, and yeah, 4 is fine. Okay, so now we're going to burn. We're going to make the orbit very high, and we're going to burn until this thing counts down. In order to synchronize, we have to go until 0. So what we're doing is we're expanding our orbit now. Okay, we're almost there. Okay, now we've got it in 2 orbits. I'm going really high because I can. Okay, now we got 1 orbit. Okay, when this bottoms out, we should be getting the 0th orbit pretty soon. There we go. Okay. So now what I'm going to do is I'm going to burn until this thing says 0. So what I've done is now I've increased our orbital period that it's exactly twice. Our orbital period is now exactly twice of what it was before. So we're going to have a 3-hour orbit, and we're going to come back. Looks like I overburned. Let's open up the retro doors.
Nose cone open.
Such a stupid thing. Well, you can now see the doors are open on the side. We're going to burn back a little bit. That should be close enough. We'd have to do a secondary, but that's fine. All right, disabling the autopilot, and let's see. We're going to be able to see something the size of Asia, given how high we're going to go. And of course, it's going to happen pretty close to night. So I'm going to 100 times the normal rate of time. Get some night lights. I think... yeah, that looks like China. China, Malaysia, Taiwan. Let's see if I'm right. Oh, nope. Nope, I am off. This is the Middle East. I was looking at this crescent here. That kind of looks like Southeast China a little bit. And when dawn happens, we'll see how truly high up we are. Yep, we can see the whole Indian Ocean now. Whoops. Okay, I almost screwed myself. We were under time warp there. Yeah, we're getting pretty close to dawn now, so I'm going to face out towards the Earth. There's 100 times. And look at how small the Earth is now. We're so far away from it. Look at how slow our orbital path has been. Remember how I said you have to slow down, or you have to speed up to go higher and slow down? That's exactly what's going on. We are slowing down. And now we can see half of the southern hemisphere now. We're really, really high. In fact, this is our apoapsis. In fact, you know what? We're so high now that we're more than the Earth's radius out from it. We're actually not quite. We're almost as far above the Earth as the center of the Earth is below the surface of the Earth. That's how high we are right now. So remember what I said about the atmosphere? There's no atmosphere up here. We're beyond the exosphere. If I go to ship info, it should actually be able to display your pressure. Yeah, nothing. Absolutely nothing. And this is highly resolute. If I go to vessel dummy up at 700 kilometers actually lists some atmospheric data. It actually has a density. 6 times 10 to the minus 14 kilograms per cubic meter and a temperature of 978 Kelvin. Remember how I said that the thermospheric temperature would go up again to thousands or hundreds of degrees? That's what it is there. That's really hot. That's like 2,000 Fahrenheit. Starting to slowly descend. And now watch our speed accelerate. We're now at 7 kilometers per second. We're going to speed up again, just like I said before. And we're getting close to the dummy. Look at this. Look at that. It's coming really close. So what I'm going to do now is... this is rather inefficient, but because the periapsis and apoapsis altitudes are so close together, we're going to do a little bit of a deceleration burn. So let's try our hand at that. We want to go prograde at this point. And if we get some outwards with this, it should be okay. But notice how long it's taking to lower that orbit. Look at how much fuel we're wasting. That's a good demonstration of how wasteful this is. You see how long this is taking? What we're going to do is we're going to change this to intersection 1. Look at how wasteful that is. We still got half of our fuel. That's how forgiving this craft is. Other items, like with the Apollo craft, if you screw up the Apollo craft by one maneuver, you're done. You are done. That's not why Apollo 13 lost the moon. It was because they closed the react valves in their fuel cells. Once you close your react valves on your fuel cells, there's certain power electrical power operations that you can't do in the future. Okay, now we've got something. We've got 138, 139, 140. All right. This tutorial is getting really long, so let me save again, and I'm going to start some higher speed operations now. So we're going to expect a spam worth of materials. Okay, so now what I'm going to do, I'm going to go all the way up to the periapsis, and now I'm going to do a prograde burn. Ooh, boy, I didn't turn off the autopilot. That's a mistake. Don't do that. I was okay at 100, but if you go to 1,000 time acceleration, that's where the ship loses control. You won't be able to gain it back. Okay, we're at the periapsis now, so what I'm going to do is I'm going to burn, and it's going to change this intersection time. Okay, there's 712. I think I overshot it. There we go. 6, 5, 3, 1. Synced. Disable, and we're going to go to 100 times. Actually, let's save again. We're going to go to 1,000 times. Show you what 1,000 looks like when you're orbiting. When you're in a low Earth orbit, you definitely don't want to go any faster than 1,000. Now, notice how the orbit materials are changing. That's called the osculating elements. A lot of time going by right now. Okay, let's see. We're 21 off now. So what I'm looking at is this DT min here. I'm going to explain how to do this when I do the ISS docking tutorial. But for the time being, I'm going to introduce you to the concepts of synchronizing orbits. You have to adjust it every once in a while due to unknowns. So we're 7,700 seconds away. 6, 5, 4, 3, 2, 22, 21, 20. And we're looking at the ship to ray, target to ray. The purpose is not to have you understand what I'm looking at. It's to understand how my movements, and that just figures it's going to be in the dark, how my movements affect what's going on. Now, I don't know if this thing has a radio beacon. If it has a radio beacon, we can lock onto the signal and adjust our speed to it. Yeah, that really sucks. This device does not have any. Well, we might be close enough for a visual. 24 seconds. Yeah, I don't know about that. Let's see how much we can change things this way. Not much. Yeah, that's not getting changed. So what happened there is I just basically should have checked that last orbit, but I didn't. This is as close as we're going to get. So what do we do? We're going to do a retrograde burn now. And that way I can show you guys. I'm starting to get really fast with this. How slowing down gets you down. So notice we're now over 8 kilometers per second, but that's because we're going so high. If I bring this into check, you should now see we're going to keep our orbits synchronized like they were before. We're bringing this back down until we get a circular orbit. And our inclination is only 0.05 degrees off. There you go. So we're pretty much co-planar and co-linear right now, so we're going to stay with each other for a long time. Okay, guys, that was pretty much it. So I've reset the simulation. I hope you guys have enjoyed this tutorial and understand a little bit how about spacecraft move around in orbits now. And I will see you guys next time. This may be the... let's see. What's next? I believe next is going to be the orbital elements. So this is the math behind orbits. So far it's been graphical. We're going to start involving the math, other than, you know, the stuff we've been doing so far. This has been Dr. Aeronautics, and I will see you guys next time. Bye-bye.